I have one extra set of the notes. Does anybody not have a copy of the class notes for the semester or want an extra copy for some reason? Otherwise, it's going to go into my fireplace. Extra set of notes, anyone? Okay. Let's take a look at these announcements. Your next homework assignment is due on Tuesday the 27th in class. I've got a couple of tips on that homework assignment that I'm going to go over in just a minute. Some suggestions that might make solving that assignment a little bit easier for you. For those students who are attending the Winter Technical Conference right now, and I presume we're going to be watching this lecture on YouTube, they should contact me to make up today's quiz. We're going to be talking about some empirical resistance equations that are found in section 3 of chapter 8. You've already been exposed to the Darcy-Weisbach equation. We're going to talk about the Hazen Williams and then a brief overview of the Manning's equation, which actually we'll get to in full strength during the second half of the semester. But I'll give you just a second to copy those announcements down into your notes. Just as a reminder, these homework assignments here, they're found in your course schedule. So it should never be a surprise to you what you see on the announcement slide for the homework assignment, because that same information for the entire semester is already on the last page of the syllabus. And so, if you want to know what assignment 3 is, or homework 4, homework 5, it's all there, and you can get a head start if that's how you like to operate. Any questions about the announcements before we move on? All right, so here are the homework tips that I mentioned, and I think that these are already in your notes. In problem 8.1, that's a reminder that when you have a really low Reynolds number, you don't actually use the Moody diagram, and Jane's equation doesn't apply. Colebrook equation shouldn't be used. There's this section of the Moody diagram where you have a linear F value, and it's linear with respect to the Reynolds number. And so it's just simply the F value is 64 divided by whatever the Reynolds number is. And in this problem, problem 8.1, the conditions will be laminar, meaning the Reynolds number is less than 2,000. Okay. On problem 8.4, you should use the Colebrook equation, and you got a taste of how to solve the Colebrook equation in the Tuesday's lecture that was posted online. What's tricky about the Colebrook equation? Implicit equation. Yeah, the F value that you're solving for is on both sides of the equation. And no matter what algebraic manipulation you do, that F value is not going to be able to be isolated. And so what that means is that you have to solve the Colebrook equation iteratively. And I'd like you to get your hands dirty and try that out at least once during the semester. So with problem 8.4, please use the Colebrook equation. Now there's a lot of ways to do that. You can do it the trial and error approach on paper if you want, and if you've got a really I don't know, glutton for punishment and you like repetitive stuff, do a trial and error by hand. You can also do it in Excel. I demonstrated a couple of ways in that recorded lecture. If you use Excel, print it out and attach that to your homework assignment. I'd like to see evidence of the method that you used. And so if you're going to use something really sophisticated like Solver or GoalSeek for solving the Colebrook equation, show me as much information as you can on that spreadsheet. I'm merciful though, so on problem 5, use the Jane equation, which is explicit rather than implicit, which means you can just solve it directly given the Reynolds number and the relative roughness. A reminder about differential manometers on problem 17. That'll make more sense when you start diving into the problem. And some parameters that I'm sure are in the book somewhere, but I just wanted to provide them for you right at the beginning on problem 26, the unit weight of water in traditional units. We all get really acquainted with 9810 newtons per cubic meter as the unit weight in SI units, but in traditional units, 62.4 pounds per cubic feet. And then the definition of a horsepower as it relates to a pump. And we'll do a problem today that will prepare you for this, but here's the relationship between horsepower and then the unit weight, flow rate in cubic feet per second. H sub P, this is the pump head, which will have units of feet, and then 550, which is a conversion factor. There's 550 foot-pounds per second per horsepower for some reason. So those are the tips. Hopefully you find them helpful, and I'll do my best to answer your questions if you send me an email over the weekend. I don't usually take like all my books home with me, but if it's something simple, I can usually respond via email, of course. If I'm in the office, I'm happy to help you even outside of my office hours. If you want to come ask me a question tomorrow or Monday, feel free. All right, so empirical resistance equations. What makes these empirical is that they're based on observation. And so here's the best of our empirical resistance equations for closed conduit flow. And you've seen it before, the Darcy-Weisbach equation. When given the option, you should always choose this equation. And you are given the option, for example, in the program Water Gems. You remember in Water Gems that one of the first things I had you do was switch it away from the Hazen Williams equation and switch it into Darcy-Weisbach. And the reason why Darcy-Weisbach is superior is that it's, number one, applicable for any liquid, not just water, whereas the other equations that we have as options are based only on water. Darcy-Weisbach equation is valid over a really wide range of flow rates, over a wide range of temperatures, and it's the most accurate for those reasons because it's valid under almost every circumstance. It's a little bit harder to use, though, because the F value is tricky to find. The F, and that's another reason why it's accurate, is that the roughness factor sort of reacts to the flow conditions, whereas the roughness factor for other equations are fixed. And we know from our previous lecture where we were looking at the thickness of the boundary layer, the boundary layer thickness changes depending on how fast the water is moving. If you have really slow-moving water and pretty laminar conditions inside of the pipe, then the roughness elements are buried under that laminar sublayer. But when the water is moving quickly and there's a lot of turbulence, those roughness elements stick out of the boundary layer and actually in contact with the bulk flow. So the Darcy-Weisbach equation can handle that complexity, but the Hazen Williams equations can't handle that complexity for a variety of reasons. Number one, it only works for water. And so remember when you did that first activity with Water Gems, I had you try out what happens with oil, what happens with mercury, find the change in pressure in the reservoir for a variety of different liquids. Well, the Hazen Williams equation technically is only supposed to be used for the liquid that has the density and viscosity properties that water does. It's also limited to that range of pipe diameters, 50 millimeters to 1850. And that's a pretty wide range, but the pipe rack that we have back in the lab, many of those pipes are smaller than 50 millimeters in diameter. So a really small pipe, you're going to get poor results from Hazen Williams because we're outside of the range in which this empirical equation was derived. Also, it's only valid technically for 16 degrees Celsius. And so if the water that you are modeling with this equation is warmer or cooler than that, you're going to have some error, additional error, as a result of the temperature not being at 16. And then also, it's limited to 3 meters per second or less. Now, why is it easy to use? Well, one thing that makes it easy to use is that this C value that goes into the Hazen Williams equation doesn't vary over flow conditions. And so there's no such thing as a Moody diagram for the Hazen Williams equation. You don't have to go through this backbreaking iterative process to calculate the F value like you do for Colebrook. You just look it up in a table. Now there will be a table that says cast iron, here's the C value. Wooden pipe, here's the C value. Concrete pipe, and so on. And it doesn't say for fast-moving water, for slow-moving water. It just tells you the C value. It's fixed. So that's pretty easy. We like easy. I'm not saying the easy is bad, but sometimes easy introduces inaccuracies. And so that's sort of why Hazen Williams is a second choice equation. if you're in a hurry, you're trying to solve something out in the field and you don't have a lot of paper, you don't have Excel to iterate the f-value calculations. If you just want to knock something out real quick, Hazen Williams equation will get you in the ballpark. Now, I've expressed it both in terms of SI units and BG units. You'll notice that here is a different empirical correction factor that varies depending on whether hydraulic radius is in units of meters or if hydraulic radius is in units of feet. But then the other thing that is unique about the Hazen Williams equation is that you can use it to solve for the head loss along two points in a pipeline. So if we have a pipe and water's flowing through it, and I'm interested in between 2 points, if my question is what is the head loss, what is H sub f, then obviously I'll use this lower version of the equation. It's just the same equation rearranged in a different way. And what you'll remember is that HF is the same as head loss divided by length is the S sub f. So that's, it doesn't look like it's just been rearranged, but it is rearranged if you substitute in the slope of the energy grade line is H sub f divided by L. And then do manipulation. Hydraulic radius, remember, for a pipe that's flowing full, hydraulic radius is the diameter divided by 4 and so on. So that's the relationship between these two equations. So the bottom one would tell you the energy loss in a pipeline for a certain velocity when the 2 points are a certain length apart and you've got a certain diameter pipe, and here's the roughness coefficient for that pipe. That's how when you'd use this one. And this version of the equation is if you don't necessarily know what the flow velocity is. And so let me give you an illustration of when you'd use that top version of it. If you had 2 tanks that are connected by a pipe, and here's location 1, here's location 2, and you want to find out what's the velocity through the pipe. How quickly is water moving through the pipe? Well, what you would know is here, the elevation difference, this value is going to be H sub f. That would be the energy loss, is the elevation difference between the two. And you know some length between them. And from that, you would be able to know the slope of the energy grade line. So this is known because you know the characteristics of the pipe, like its diameter. Then you could know the hydraulic radius, and then you'd just look up the roughness value out of some table. And so using the Hazen Williams equation this way, you'd be able to predict the velocity of water flowing through a pipe when the slope of the energy grade line, S sub f, is known. So it's pretty handy. Occasionally there will be questions on the FE exam that are related to the Hazen Williams equation. Because it's easy. On the FE exam, you take it on the computer, you've got on average about 3 minutes per question. I mean, sometimes you can't even find the F value in 3 minutes. And so if you're having a hydraulics question, it's easier to write one using the Hazen Williams equation than it is using Darcy-Weisbach. So you can anticipate both, but it's on my mind because just at the technical conference they were mentioning how of our 7 seniors who took the FE exam on January 10th, all 7 passed. So you guys are going to have to step it up to continue that trend next year, right? Everyone needs to pass. All right. Manning's equation is our third empirical resistance equation, and what all of these are doing is just basically saying how does shear stress cause energy loss? Remember that if water is moving to the right, the pipe is pushing on the water to the left. It is resisting the movement of that water. And so these empirical formulas try and predict how much energy is lost based on the characteristics of the pipe and the characteristics of the flow. Now, Manning's equation we usually only use for open channel flow, but technically it can be applied for the situation where you've got closed conduit pressurized pipe flow. It's used to solve for the velocity of flow in a pipe, where you've got the hydraulic radius as a shape parameter, the slope of the energy grade line, which is telling you how much energy loss there is for a certain length of pipe. But then now the roughness value is assigned the variable n. And let me show you a range of typical n values for different types of pipe. Actually, this is n values on the right, Hazen Williams C values on the left. So if a pipe is rough, has lots of rivets and roughness, then you have a big n value. A smooth pipe has a small n value. So you don't see that too well on the values that are shown here, but when it comes to Manning's n, rough goes to a big value, smooth goes to a small n. The opposite is true for Hazen Williams. So for C values, and the way that you can know that is a new pipe has a C value of 130. So smooth pipes are generally more smooth when they're new than they are when they're old and have started to corrode a little bit, or if there's mineral accumulation, then they become more rough. So smooth is a big C value, and a rough pipe has a small C value. Let's look back at the equations and see if that makes sense. Okay, so first with the Hazen Williams. If we think that a rough pipe should have a small C value, look at the equation. If you have a small c, since that's in the denominator, then that will increase the head loss for a given pipe section. But if you have a smooth pipe when you don't expect there to be very much resistance to flow, and you're not losing as much energy as the water moves through that smooth pipe, then a big C value, since it's in the denominator, is going to give you a smaller energy loss, H sub F. Whereas the opposite is true for the Manning's equation. For the Manning's equation, since it's also in the denominator, if you want it to be the velocity to be high, a high velocity, you're going to have a smooth pipe, and so a smooth pipe, small n, the Manning's equation as it's expressed here, a small n value, meaning smooth pipe, will give you a bigger velocity for the same slope of the energy grade line, SF. All right, let's go through and consider using all three of these equations at the same time and estimate the head loss over a 500 meter length segment of pipe. And this is just to give you an idea of the magnitude of how broadly these three estimates can diverge when used for the same pipe conditions, the same flow conditions, and what I've selected here, the flow rate and the pipe diameter, this is valid for all three of the methods. All three of the methods technically should be able to give you a reasonable estimate. So we'll begin with the Hazen Williams. Okay, in the Hazen Williams equation, this particular pipe, ductile iron pipe, for new ductile iron, if we go back to the table, the 130 is a typical C sub H for new unlined ductile iron. Okay, so C sub H is 130. The diameter of the pipe is 0.150 meters. And water is flowing through it at a velocity of 1 meter per second, which is less than the limit. The limit that we're told for Hazen Williams equation is that velocity should be below 3 meters per second, and it is in this illustration. Okay, the pipe length is 500 meters. And what else do we know? Okay, that's it. So how much head loss is there? The h sub f, 6.82 times L divided by D to the 1.17 power V divided by C sub H to the 1.85 power. And what's magical about 1.17 and 1.85? I mean, are these like fundamental concepts of the universe, like governing numbers, you know, like have special significance? Like we all know that 3.14159, that's not just some random stupid number. It has meaning. What about these ones? 6.82, 1.17, 1.85, where does that come from? That's just, those were identified when the equation was made through the process of empiricism, which is a lot of observations were relating head loss and some parameter. They probably were playing around with different velocities. And they had observed data that was like this, and they tried with Excel or some other program to do a least squares method of fitting a curve to the data, and the equation that fit the data best had these exponents and coefficients that went along with it. So it's nothing fundamental. It's nothing that ties into the underlying physics of resistance or shear stress, but these are just empirical factors that makes the data and the equation fit observations. So sometimes we wonder, like, how do the units work out? Because I always emphasize, include the units in your calculations. Well, they don't work out in an empirical equation like this. This is not dimensionally homogeneous. Okay, so let's substitute the numbers into the equation. 6.82 times the length, which is 500 meters, divided by the diameter, 0.15 meters to the 1.17 power. And then our velocity was 1 meter per second. And our C value of 130, all of that to the 1.85 power. Put that in your calculator. See what you get as the head loss here. It is for 500 meters of pipe length. Should be 3.85 meters is the head loss that you get according to the Hazen Williams equation. You notice that when I'm doing my calculations on the calculator, I kind of try and do it in steps, and I write down the intermediate steps so I can double check my work later on. When I was in your shoes, when I was an undergraduate student, I got in the habit of triple checking my calculations just because I guess I was sloppy and made mistakes often enough that I needed to do it 3 times to feel confident that I'd done it right. And so when you're doing your calculations over and over, it helps to break it up into pieces and then make sure that when you're checking your calculations that the pieces match each time you go through it. So you can see that that's what I've done here. So ultimately, the head loss over 500 meters of pipe length will be 3.85 meters of head. Now what about Manning's equation? Manning's equation isn't used for pipe flow very often, at least not pressurized pipe flow. It's used when the water flowing through the pipe is only partly full. Usually, if we're using Manning's equation in a circular conduit, it's like when the water's only part of the way up. So that should give you an idea of how good Manning's equation is going to be at this prediction. Let's give it a shot. H sub f is 6.35 n squared L v squared divided by d to the 4/3. That's totally different than the equation I showed you just a minute ago. Like, where does that equation come from? Well, again, here's Manning's equation in terms of velocity and S sub f. Remember, S sub f is hf divided by L. So what I did was I substituted into this SF term h sub f divided by L, and then I rearranged the equation to solve it in terms of hf. And that's what we get. We're using in this problem SI units, and so I used this equation on the left when I was doing it. All right, the N value for this pipe is 0.013. So with the substitution, 6.35 times 0.013 squared times 500 meters, 1 meter per second squared, divided by the diameter 0.150 meters to the 4/3 power. Okay, so again, doing it in intermediate steps, 0.5366 in the numerator, 7.97 times 10 to the negative 2 in the denominator, 6.73 meters is how Manning's equation predicts what the energy loss will be. That's a pretty big difference. They should have said the same thing, but they didn't. Of the two, Hazen Williams equation is more reliable for pipe flow, like we have here. Finally, we'll do Darcy-Weisbach equation. And we'll find our F value according to the Jane method. Okay, so Darcy-Weisbach. First of all, we need to know the Reynolds number in order to substitute that into the Darcy-Weisbach equation. We have to know F. There are two main terms in the Jane equation. There is the relative roughness term, this K sub s, or epsilon as your book calls it. The ratio of the equivalent sand roughness to the pipe diameter is one of the terms, and then the other term has to do with the flow conditions. And so this term is basically the pipe conditions, and this term is the flow conditions. And you remember from the Moody diagram that there becomes a point that the flow conditions don't change the F value anymore. To the right of that dashed line, it's a plateau. You know, the line becomes straight. It's curved for a while. It's curved to the left of the line. There's a curve, but then to the right of it, it's flat. And that is because if you have a really big Reynolds number, this term goes to 0. Okay, so in this case, we need to know our Reynolds number, and we're going to do that with the velocity times the diameter divided by the kinematic viscosity. This is water that's flowing through the pipe. We don't know anything about its temperature, so we'll just use the standard 1 times 10 to the minus 6th meters squared per second, which is a typical kinematic viscosity for water at room temperature. And then for the flow velocity, it's 1 meter per second, and the diameter of the pipe, 0.15 meters. The Reynolds number, therefore, is 1.5 times 10 to the 8th. And Reynolds number, 10 to the 5th, not 10 to the 8th. 10 to the 5th. The Reynolds number is unitless. So if we put that into the Jane equation to get our F value, we have 1.325, and in the denominator the logarithm of 0.26 millimeters, which is the equivalent sand roughness for this pipe, ductile iron, and then 3.7 times diameter of the pipe, 150 millimeters. Now I've been putting 0.15 as the diameter of the pipe everywhere else till now. But the reason why I'm putting 150 is I have to have the same units in the denominator for pipe diameter that I use for the equivalent sand roughness in the numerator. So if you wanted to put in 0.15 meters, then it's important for you to express this K sub s value also in meters, or else you're going to get a big error. And then 5.74 divided by the Reynolds number, 1.5 times 10 to the 5th power, and that's to the 0.9 power. Close the logarithm, and then square the denominator. You've probably only solved the Jane equation a couple of times. You're going to get used to solving it a lot. So see what you get for the F value under these conditions if you haven't already. Use your calculator to calculate F. Get some practice doing that. Okay, when you're finished with the Jane equation, you should get that the F value is 0.0240. And this is a really good illustration. When you do these three methods back to back, it's a good illustration of why the Darcy-Weisbach equation is more accurate, is because think about all of the effort that went into just finding the F value. And we haven't even started the substitution into the Darcy-Weisbach equation itself yet. We're still just focusing on how rough is the pipe for these conditions. In the other two methods, how rough is the pipe in these conditions isn't a question you even ask. It's just, here's the roughness value for the pipe. It's not condition specific. But now that we have the F value, we can substitute it into Darcy-Weisbach. H sub F is FLV squared divided by D2G. So 0.0240, which is the F value, our length of 500 meters, the velocity squared, 1 meter per second squared, divided by the diameter, 0.15 meters, and then 2G, 2 times 9.81 meters per second squared. Okay, we do that and end up with 4.08 meters. So the Hazen Williams equation was too low, Manning's equation was too high, Darcy-Weisbach equation was just right. All right. Any questions about this illustration? Yep, that's right. If you got the time and have the computational resources available, you know, if you can find the F value, go for it. All right. We've got some time, and so we are going to solve this one with the computers. And if you brought a laptop today, great. Go ahead and get it out. If you didn't, grab one of the computers out of the cart. I didn't think that we'd have enough time to have everyone using the computers. Now, we've only got like 10 or 11 of those tablet computers, so you're definitely going to have to double or triple up on using them. But we're going to go through and solve this iteratively using Excel. So I'll give you a minute to get set up with the computers. Okay. We have water flowing between two reservoirs. The water is flowing from the lower reservoir to the higher reservoir. And obviously the only way you can get water to flow uphill is if you use a pump of some sort. So that's what they're doing here. This symbol with the P means pump. And what we know about this pump is that it's a 10 horsepower pump, and the length of flow is 800 feet. It's cast iron pipe, and that tells us the equivalent sand roughness of the material. We know the flow rate that's required, and what we're trying to do is size the diameter of the pipe. Everything is known except for how big the pipe is going to be. And this is an unusual problem where actually the head loss is going to be fixed by the characteristics of the pipe. And so let me show you what I mean by that. Water's flowing from 1 towards 2, so it's going to the upper reservoir, and the dimensions that are given of 35 feet define the delta Z. So delta Z is 35 feet, is how much higher this upper reservoir is than the lower reservoir. And we can start off with the energy equation, because the energy equation always applies. P1 divided by gamma plus Z1 plus V1 squared divided by 2G plus HP. A lot of the time when we're writing the energy equation, we don't write the pump head term because there's no pump. In this case, there is a pump, and it goes on the left-hand side of the equation. Is equal to P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus HF. Okay? Remember that head loss is friction losses plus local losses. Friction, local losses. In this problem, we're neglecting the local losses, and so it's just the frictional losses that are being considered. And so that's why I've substituted here HF instead of the broader term HL. I could write HL, but in this case there's no local losses, there's only friction losses, and so I'm just going to put the HF in there directly. So let's take a look at what are the conditions at location 1 and what are the conditions at location 2. Okay? If it's a tank that's open to the atmosphere, then the pressure of the water at the surface is the same as the atmospheric pressure. And so gauge pressure, if we're using the atmospheric pressure as our baseline, then that means the water pressure here at the surface is 0. So the pressure head term cancels out of the equation on the left and also on the right. The pressure of the water at the surface of this reservoir on the right is just atmospheric. It's the same water pressure at the surface as is the air, so we cancel out the P2 term. Z1, let's let that be equal to 0, and then we will call Z2 35 meters. We'll use the water surface at the tank on the left as our elevation datum. Okay, V1, this is a big reservoir, and the water level maybe is going down slowly, but the water essentially is stationary. And so we're going to say that the V1 is 0, and the same thing is true at 2. Now we're not talking about the velocity in the pipe. The velocity in the pipe is significant, but V1 just means at a location. It's not talking about in the pipeline. It's talking about the velocity at a point. And so V1 is 0, and V2 is also 0, because at this location inside the tank at the water surface, it may be rising ever so slowly, but so slowly that we don't need to worry about it in this problem. So what we're ending up with is that the pump head is equal to 35 meters plus h sub f. H sub f is going to be determined by how much pump head is being put out by this pump. So let's think about what's going on with the pump. We already know how much power it has. The power of the pump is 10 horsepower. If we want to convert that between pump head and horsepower, we have this equation. It says that the power of a pump is equal to the unit weight, the flow rate, and the pump head, and then 550 is just a units conversion. Okay, so if we rearrange that to solve for pump head, H sub P is 550 times horsepower divided by the unit weight times the flow rate. Okay, 550 times 10 divided by 62.4 pounds per cubic foot, and the flow rate is 1.5 cubic feet per second. So the pump head, if we do those calculations, it's 58.79 feet. The physical interpretation of this pump head is that this pump is essentially lifting the water 58.79 feet. It's having the same effect. You know, it's not actually physically lifting the water, because you can see that, you know, this pump is just in one location. So it's not like it's actually physically lifting the water and then it's flowing downhill. But it's kind of like saying, if you had a reservoir, how tall would that reservoir be? You know, how much pressure is the pump adding? The units work out because a horsepower is 550 foot-pounds per second. Yeah, because it looks like they don't work out. But I didn't write the 550 foot-pounds per second per horsepower. And let me do that just for the sake of completeness. 550 foot-pounds per second per horsepower times 10 horsepower. There we go. I think they work out now. Other questions? That was a good one. How do the units work out is always a good question. All right. All right, so pump head is kind of an abstract term for a lot of students. You're thinking like, what does it even mean? Basically, the physical interpretation of pump head is the way the pump works is by adding pressure to the system. And it's adding the same amount of pressure as if it was lifting the water 58.8 feet. That's the easiest way I can express it. So if that's the pump head, then what does that tell us about how much head loss there is? H sub F is going to be 58.79 feet minus 35. Oh, I wrote meters. I should have written feet for the delta Z. It says feet over there. Right. Feet. So head loss, there is 23.79. And what that means is after lifting the water 35 feet, the pump has still added enough extra energy that there is 23.79 feet available to satisfy friction losses. The more energy the pump adds, the faster the water is going to go. If that pump was only like a 9 horsepower pump, then it wouldn't have added as much pressure and the water wouldn't flow as fast. So the more energy the pump adds, the faster the water is able to go. And so what we're saying is that this 23.79 is going to be equal to FLV squared divided by D2G. Because this is H sub F, and the Darcy-Weisbach equation is H sub F is equal to those terms. And so why have I asked you to get Excel out? It's because every time we change the diameter, it's going to change the F value, and it's going to change the velocity. And so that could be a really tedious problem if you try and iterate that by hand. You know, the main thing is how big should the pipe be? If we've got 23.8 meters, oh no, not meters, feet of head available to push that water along, and the flow rate, we wanted a certain flow rate. It's not like any flow rate will do. We want Q to be equal to 1.5 cubic feet per second. And so we have to find out the perfect pipe size that's going to make this all work. And remember, every time we change the pipe size, we change the velocity, Reynolds number, F value. So there's a whole chain of consequences that we have to be ready for. Okay, so we've got 6 minutes. Let's see if we can knock this out in 6 minutes on Excel. Step 1, start Excel. Wait for it. While it loads, any question about what I've been talking about? Understanding pump head, etc. Good question. Yeah, I don't know. You pick something. You got to have some random guess to begin. I guess random isn't the best option. You know, just like maybe in some middle value that you think is reasonable. All right, so let's do this. There's horsepower, which I knew was 10. There's the K sub S value in terms of feet. This is the equivalent sand roughness. If I look that up in the table that's provided in the book, this pipe has a roughness of 0.00085. And then the unit weight, gamma, in terms of pounds per cubic foot, is 62.37. Don't worry about getting the exponent and, you know, inserting the symbol. We don't have time for that. We're going to have to do the quick and dirty approach. Okay, there's kinematic viscosity, which has units in traditional is feet squared per second. And the typical kinematic viscosity for water is 1.22 times 10 to the minus 5. So I could type in 0.0000 a bunch of times to get what I want, or you can just key it in as 1.22 E minus 5. And then it automatically assumes scientific notation for the kinematic viscosity. Okay, the Q that I know in terms of cubic feet per second, we want it to be 1.5 cubic feet per second. And the pump head, HP, in units of feet that we've calculated already is 58.79. And by the way, if I'm going too quick, remember that this recording is going to be on YouTube in about 30 minutes. It'll be posted on the class website. So you can go through and watch this again if you're not able to keep up. So the HF in terms of feet is 23.79. G for traditional units, feet per second squared, is 32.2. And the length of the pipe is 800. Is there any questions? We've still got 3 minutes. Don't cut me short. All right. So F value. This is our initial guess. And I'm going to be using the Jane equation here. And so we don't yet know what is the flow conditions. And so I'm just going to base the F value on the K sub S to D part of the Jane equation. So equals 1.325 divided by the ln of K sub S divided by 3.7 divided by D, which I'm going to guess right here. And then I need to square that. Okay, so here's my D value that is going to be my initial guess, and let's say that it's 0.4. Okay, so I have some guess F value, the area in square feet, the velocity in feet per second, and then the Reynolds number that's going to come from that. All right. I thought we'd be able to get through it. Doesn't look promising. So what we're going to do is pause this, save your work. If you're with me so far, save your work. We'll come back to the same example on Tuesday. But you have a homework problem that's similar to this. You won't necessarily have to iterate on Excel to solve the homework problem. But what you should remember is how to convert between horsepower and pump head. And I already illustrated that part on the board. All right, see you on Tuesday.